So year 9, as part of revising all your physics content from this year, we're going to go over the topic on specific latent heat. Now, in terms of your success criteria, we're hoping for you to define what the term specific latent heat means, describe the difference between specific latent heat, which is SLH, for fusion and vaporization, and hopefully you should be able to calculate specific latent heat for fusion and vaporization with energy and mass using a formula triangle. And lastly, you should be able to analyze and interpret heating and cooling graphs. Now, just as a quick starter, you've got the three states of matter: solid, liquids, and gases. Now, a little bit of revision from last week, but what I'd like you to just remind yourself of is the terms that we use. For example, if a solid turns into a liquid, what do we call that process? Now, hopefully you should be saying melting. Okay, so just try and remember or remind yourself of the different terms we use for when the states of matter turn into each other. Now, if you just take a quick look at that diagram, inside the liquid, the gas, and the solids, you can see all the molecular bonds. You can see all the particles and how they're all actually connected to each other. So we know from revision, solids are regularly packed, they're close together, and they're vibrating. Their intermolecular forces of attraction are very strong. That's why they don't physically move or break at this point. However, when they become a liquid, some of those intermolecular bonds actually do start to break, and you can see the particles are still vibrating, but some of them are starting to loosen a little bit. And then obviously when it turns from a liquid to a gas, you can see all those separate particles whizzing around with loads of kinetic energy. Okay, so as I said, just pause the clip here for a minute just to remind yourself of those different terms. Now, hopefully, this is what you would have said. So from a solid to a liquid, obviously, we know it's melting. When a liquid turns back into a solid, we know that as freezing. However, when a solid turns into a gas, we call that sublimation. And when a gas turns back to a solid, which actually is quite hard, it's called deposition. And if a liquid turns into a gas, we term that as vaporization. However, if a gas turns into a liquid, we call that condensation. Okay, so let's go through some key words, which is quite important that you are able to recall. So latent heat, which is the new key term, is the energy needed to change the state of a substance without a change in temperature. The energy supplied is used to change the internal energy store of the substance. Now, what we're basically trying to say is if I had 1 kilogram of ice at 0 degrees Celsius, if I wanted to melt it down to a kilo of water, there will be a certain amount of energy that is required to break those bonds. Okay, so let's have a look here. The latent heat for melting is called specific latent heat of fusion. Now, that can be used for melting and it can also be used for freezing. The other key term is the latent heat for evaporation or even condensation. We call it the specific latent heat of vaporization. So you can see LF is for fusion and LV is for vaporization over there. Okay, so if I wanted to convert a kilo of ice at 0 degrees Celsius to 1 kilogram of water at 0, I would actually have to call this energy required the specific latent heat of fusion. Now, because I've got 1 kilogram of water at 0 degrees Celsius and I want to actually turn it into water vapor, that's when we use the term specific latent heat of vaporization. Now, to put it into context for you, okay, specific latent heat of fusion for water is 336,000 joules per kilogram. Now, what that basically means is that you are going to need 336,000 joules of energy to turn 1 kilogram of ice into 1 kilogram of water with no temperature change. So literally what you're trying to do is break the bonds from the solids going into a liquid. So that's where latent heat comes from. Now, just remember the key point at the bottom in yellow. So I've just put that as a reminder. Specific latent heat of fusion only refers to melting and freezing. However, specific latent heat of vaporization refers to the process of evaporation and condensation. So let's put that information into a question for us to apply our knowledge. 5 grams of gold is being melted to make a ring. Once the gold reaches its melting temperature, how much heat energy is needed to melt the gold? So because we're talking about melting, hence we need to think about the latent heat of fusion for gold. Now, this number here is given to you in the exam. So for the actual solid block of gold to melt, you need to provide 64,400 joules per kilogram of heat to actually break that down. Now, there is a formula that you need to actually be able to use, and it's the energy to change state in joules. So if we want to turn a solid into a liquid, or a liquid into gas, or a gas into solid, we would use this particular formula. So you can rearrange the formula and put it into a triangle, which we'll do in a minute. But let's just focus on this particular question. So to work out the energy to change the solid gold to liquid gold, we have to find out what the mass is in kilograms, and we need to times it by the specific latent heat, which should also be given to you in the question. So in this case, we know the mass is 5 grams because we got that from the question. And don't forget, we have to turn it into kilograms, okay? So that would be 0.0005 kilograms times 64,400 joules per kilo, because again, we got this digit from our question, and that gives us an answer of 322 joules, which means you need 322 joules of heat energy to melt 5 grams of gold. So just now we just did a basic formula to find out the specific latent heat of fusion for gold. Now, we can put any formula into a particular triangle, all right? So the formula that we just used just now was quite straightforward because we used this formula here. Specific latent heat of fusion times mass, and we were able to work out the amount of energy required to turn solid gold into liquid gold. Now, if we actually put the information into a formula triangle, okay, you've got energy at the top, you've got specific latent heat of fusion in the bottom left, and you've got M, that stands for mass, okay? So for example, if you were being asked to find out the specific latent heat of fusion for a question, all you would have to do is do energy divided by mass. If, however, you wanted to find mass, you would do the energy divided by the specific latent heat of fusion. And don't forget, within the question, they will give you this data, okay? So let's have a look at this particular worked example. Now the question says 398 joules of energy is needed to turn 500 grams of liquid nitrogen into a gas of minus 196 degrees Celsius. Calculate the specific latent heat of vaporization of nitrogen, okay? Now, notice instead of the specific latent heat of fusion, they are talking about vaporization because we are talking about converting a gas, okay? So step one, write down what you know and what you want to know. So let's write down the energy. So first of all, we know that the energy required is 99,500 joules. Now, this bit of information is given to you because it's basically saying for nitrogen to actually vaporize, that's the amount of energy that is going to be required. The mass we know is 500 grams because that was in the actual question. And again, don't forget, we need to convert kilograms to grams, and I have put a bit of a conversion chart here, so it will remind you how to do your conversions, okay? And the information that we're actually being asked to find is the latent heat of vaporization. That's the bit we don't know. So if we use the triangle to decide how to find the answer, all we need to do is put the energy, which we know, we need to divide it by 0.5 kilograms. And if we divide those two numbers together, we should get 199,000 joules per kilogram as your final answer. So the final answer you could write is the specific latent heat of vaporization of nitrogen is 199,000 joules per kilogram as your final answer. So now we've actually gone through how to use the formula triangle. What I'd like you to do is just pause this clip and head over to the Google quiz questions that is titled specific latent heat. Now, these are the questions that I've actually put on as a multiple choice activity. So once you've actually completed those using the formula triangle, then come back to carry on the lesson. So well done for doing those questions on the Google quiz, guys. All right, so let's just try and get ourselves refocused again. Now, what I want to introduce you to, and again, you most probably would have remembered this from last year, is something called heating and cooling graphs. Now, if you look at the graph on the screen, all right, and just take a minute to understand what this graph is actually showing you. Okay, so I'll just give you a couple of seconds just to have a look at it first. Okay, so let's give you a bit of a hand if you're slightly confused, okay? So this graph shows us what happens when solids, liquids and gases change state. It tells us what happens to its temperature as we add different amounts of heat or as we cool it down, okay? So let's start right at the bottom here where solids are, okay? So as heat energy is added to a solid, obviously we know it's going to become a liquid because it's actually going to melt. Okay, now the interesting thing is when a solid becomes a liquid, all those intermolecular bonds are starting to separate. So as you can see, there's actually a straight line on the graph which shows us that actually the temperature isn't rising. At that point, the intermolecular forces between the particles are starting to separate. Then once it hits the liquid point, the liquid will then start to condense into a gas. So it will go from a liquid to a gas. So it'll change state. But again, if you notice at the top, there's a straight line. So it plateaus and the temperature doesn't go up anymore because at that point, again, the intermolecular forces between the particles are breaking up totally when we're turning a liquid into a gas, because as we know, those particles have loads of kinetic energy and they've broken all their bonds. Now, this is basically a heating and cooling graph. So when we read it from down to up, we look at it as a heating graph because you're going from solid to liquid to gas. However, if we look at it from the top where it's a gas and it goes down back to a solid, so when we're showing freezing and condensation, that's when we call it the cooling graph. But what you really need to take away from this is as substances melt, all the heat energy added is used to change the state of the substance, but the overall temperature does not change. That's why we see those flat periods on the graph. When all the substance is melted, the temperature will then rise until the boiling point is reached. Again, heat energy is now required to change the state to a gas, but we don't want any temperature change. So whenever we're talking about specific latent heat of fusion or vaporization, what we're actually talking about is what happens to those intermolecular forces between particles when they need to change state. So again, this picture obviously which I showed you during the starter, you need to bear in mind that at different changes of states, there needs to be different amounts of energy to either break those bonds or to remake them. So let's look at this graph, very similar to the one that I showed you just now on the previous slide. But if you notice, the two extra bits of information that they've put on is where the approximate melting point and where the approximate boiling point of water actually is. So what this graph is showing you is when we have ice, so we just have, let's say, an ice cube, okay, at this point here, as we increase the temperature, we all know that ice will turn into a liquid at its melting point. Okay, now again, the temperature during that change, when the solid is changing to a liquid from here to here, the temperature is not rising. It flatlines because the temperature is not going up because it's being used, that extra heat is being used as the latent heat of fusion for that melting to occur. Then, however, when the liquid of the water has transformed itself, it will carry on going up in temperature as we add more and more heat until its boiling point of about 100 degrees Celsius. We know that because water boils at that temperature. And again, the temperature will plateau because we're not increasing the overall temperature. Again, we're actually looking at the latent heat of vaporization because the energy is being used to break down the bonds further, going from a liquid to a gas, and obviously once it hits that gas phase, the temperature will obviously continue to rise. So let's have a go at applying your knowledge to this graph question. At what temperature does water freeze? Now we know if a liquid turns into a solid, we can see from the graph that that happens at 0 degrees Celsius because the graph is flatlining, because that's where the specific latent heat of fusion is occurring, because those intermolecular forces between the particles are starting to reform again. And they also want to know at which temperature does the water boil, and when obviously the liquid turns into a gas is this phase here because it's flatlining. So it's approximately 100 degrees Celsius. That is the temperature at which water boils. Question 2 says, between which temperatures on the graph is the water a solid? So between which two temperatures is a solid? We can see it's at -40 to 0 degrees. And in terms of a liquid, the temperature is from 0 to 100. And in terms of a gas, it is from 100 degrees Celsius upwards. And last question, what is happening to the substance when the graph goes flat at 0 degrees and 100 degrees Celsius? Well, we've just said earlier that at 0 degrees, that's when the intermolecular forces of the particles are actually forming to go from the liquid to the solid. And at 100 degrees Celsius, we know that's when the liquid turns into a gas, hence why the graph has gone flat, because that is the specific latent heat of vaporization. Now we've gone through how to calculate the specific latent heat of vaporization and fusion, and we've also been able to analyze different graphs. What I'd like you to do is to pause the clip on this slide and have a go at the questions in front of you. So just pause the clip here and have a go at these few questions. Okay, let's see how you did then, guys. A boiler is being used to heat water. The graph shows the temperature of the water every 5 minutes. So the first question says, what state is the water in between points Q and R? So between 40 degrees Celsius and 100 degrees Celsius, what is the state of matter? Is it solid, liquid, or gas? So hopefully you would have said the answer is liquid, because between 40 degrees and 100, that is water in its current state. At which point does the water begin to boil? So we know that water has a boiling point of 100 degrees Celsius, and we know that because the graph has flatlined, which means that is the point of specific latent heat of vaporization. Now, what state is the water in at 110 degrees Celsius? We know that from a liquid, the next change of state up would be for it to go into a gas. The last question says, candle wax has a latent heat of fusion of 200,000 joules per kilogram. If the candle is at its melting temperature, how much heat energy is needed to melt a 250-gram candle? So they've even given you the formula, so it makes it a little bit easier. So energy equals mass times the latent heat of fusion. So the mass of the candle was 250 grams. We have to convert that to kilograms, don't forget. And then we just times it by 200,000, which we got from the question up here. And the total energy should be 50,000 joules of energy is required to melt that 250-gram candle. So now that we've come to the end of the lesson, let's have a look at your success criteria. So were you able to define what specific latent heat means? And we did that right at the start, so that should be yes. Describe the difference between the specific latent heat for fusion and vaporization, and we did do that because we talk about fusion when we are going between a liquid to a solid or a solid to a liquid, and for vaporization is when a liquid turns into a gas or a gas turns into a liquid. Okay, so we've done that as well. You should have now be able to use the formula triangle to calculate the energy, the mass, and the specific latent heat for vaporization or fusion, which we have done, and we have done some questions on that. And lastly, you should be able to analyze and interpret heating and cooling graphs, which we just did on the previous two slides. So hopefully you feel like you've actually achieved quite a lot this lesson. Now, just to end the lesson on a little bit of a high, there is a YouTube video that I have put in the playlist for today's lesson, and it actually teaches you how to make instant ice slushy sculptures. It's all to do with the different temperatures of how we can actually turn a liquid into a solid very quickly, as long as you freeze it at a certain point. So have a look, go onto the actual link and see if you can challenge yourself to actually create instant ice slushies for this particularly hot heat wave they're having at the moment.